Good morning, dear students. Today we'll understand an expression, or we'll learn how to obtain an expression for magnetic field on the axis of current carrying loop. I just considered a loop. The loop is only one single loop. You can call it as a single loop. Single loop. With respect to this origin, it is at a radius r. R is the radius of the loop. And this loop is present in, of course, I can say y and z. It is in yz plane. The loop is present in yz plane. Yes. Now, if I consider a small current element, what is current element? This whole loop carries some current, and think the direction of a current is in this way, anti-clockwise. Yes, like this. And here it is like this. You can have a clockwise also. Yes, if I consider anti-clockwise, if current is going in this direction, if I consider a small element here, it is called di. Our main intention is to have an expression for magnetic field on the axis of a current carrying loop. This x-axis acts as an axis of this circular loop. Means this axis is perpendicular to the loop and this loop is present in yz plane. I repeat, x-axis acts as axis of a loop. Axis of loop. This x-axis is perpendicular to the loop and the loop is present in yz plane. Now, since current is flowing, let's call it as this arrow mark means I. I is a current in the circular loop, only single loop. Now, consider a small element. The total length of the loop, of course, we'll calculate. Since its radius is r, the circumference is 2 pi r. So, if this is the small element and if I put an arrow mark, this indicates, yes, the direction of a current element. It is called IDL. Here I have taken a small strip. Here I have taken a small strip. The length of the strip is current carrying wire is DL. And since current, I need to consider a vector concept IDL. And because of the small current in this part of the wire, what is the magnetic field at this point? Because the expression is magnetic field on the axis of a current carrying loop. This loop is carrying current. Take a small part of it and first calculate what is a magnetic field. Because of this loop, what is the magnetic field at a point P on the loop? Just connect it by some line. You can have a line. Yes. The moment I reach a point here, this is a straight line. And this line, of course, as I said, YZ plane, you have one more plane where this is perpendicular and this is, with respect to this point, it is at a distance small r. Capital R is taken for radius of the loop. Small r is the distance between the current element and the point P, where you are interested in writing an expression for magnetic field at a point P, magnetic field at a point P on the axis of a current carrying loop. Now think the direction of this magnetic field is like this. It's a vector. And with respect to this ideal, this is r vector. It is called a displacement vector. This is perpendicular. Whereas this is in xy plane. This vector is in xy plane. This current element ideal is in yz plane. This whole loop is in yz plane. This r is a displacement vector from the point where the current is flowing. It is called ideal. You have magnetic field here. Call it as dB. Oh, why dB? You have taken a small element dl. dl means corresponding magnetic field is called dB. Now you resolve magnetic field in two components, one horizontal, one vertical. This is called magnetic field vertical. So since current is flowing the whole loop, I can consider a point here. I can consider the whole strip. So to make it symmetric, since I have taken here, if I take a diametrically opposite current element, so I'll get one more diametric opposite. So for this, it is like this. It is from, and I can have a similar current element. This is again ideal. Because current is flowing here also, current is flowing here also. Since I have taken a current element flowing in this direction, because of this you have magnetic field, and because of this current element, again you have magnetic field, which looks like this. You can write x-axis, and think, just to make it meaningful, I just have a line, a vector quantity. This is again, this dotted line is a magnetic field. If I connect it again from here to here, like this with the help of a scale. If I connect it from here, it looks like, yes, this is ideal, a small current element, diametric opposite. There is again, now the direction of current is here in this way, and the direction of current is this way. Because of this direction of a current, again this distance between I element, ideal, and this is again R. Now the magnetic field is in this fashion, it is dB. Again, if I consider this magnetic field into two components, vertical component, horizontal component, horizontal is here, it is called dBx. You call it as dBx1 and it is called dBx2. So this vertical component are equal in magnitude. This dBl vertical component are equal in magnitude. You can call it as 1, you can call it as 2. Equal in magnitude, opposite in direction, hence they nullify, they cancel each other. What happens? When you consider a small current element, you'll get a magnetic field at this point. The magnetic field at this point will be like this in this direction. If I consider this vector into two components, horizontal component, dBx, and dB perpendicular, because of this current element. If I consider similarly another current element, which is in this direction, ideal, and the distance is same R, what is the magnetic field here? Again, the magnetic field is in this fashion. It is up, it is down. If I split into two components, horizontal component, vertical component, the vertical components are equal in magnitude. Opposite in direction, you can call the component, the small element 1, the small element 2. And this 1 and 2 are equal in magnitude, opposite in direction, hence they cancel each other effect. And similarly, if you go on considering any current element on this particular loop, all the vertical components cancel each other. All the vertical components cancel each other. Only horizontal components are added up. All the horizontal components are added up. So I took only one component and then I took diametrical opposite components. When you have a loop, you have such diametrical opposite components where all the vertical components are equal in magnitude, opposite in direction, they nullify. Whereas the vertical component, of course, the magnetic field is always perpendicular. You need to convert into vertical component, horizontal component. The vertical components nullify. This is called vertical component. So you can say this is a vertical component. All the horizontal components like dBx, because this component is along x-axis, hence I have written as vertical component is written as dB, the elemental magnetic field. Small element, corresponding magnetic field. Elemental magnetic field is along x-axis. We know that from Biot-Savart's law, in the last class we studied, because of a current element, ideal, what is the magnetic field here? The magnetic field is dB, which is joined to vertical component, horizontal component. If I consider magnetic field, this is dB. Here, dB is given by Biot-Savart's law. Mu 0 divided by 4 pi, current element I, dl cross R. This is current element. It has a cross product because the direction of dB is dictated by the cross product of ideal into cross R. In the denominator, you have R cube. So this gives me another, when you go for a cross product, you have a simplification process. It is, since it is 90 degree, since theta is 90 degree, then I will be taking dB equal to mu 0 divided by 4 pi I dl divided by R square. This is the first part, call it as equation 1. Now if I write this is an angle theta and the angle between this vertical and this is 90 degree, this becomes 90 minus theta. Now this vector dB and this vector, this I can say displacement vector, R is called displacement. The angle between this vector, magnetic field vector, I repeat, magnetic field vector and a displacement vector is 90 degree. then this angle naturally becomes theta. This becomes 90 minus theta. This becomes a theta. This is a concept. I repeat, ideal, the angle between R is 90 degree, and the angle between dB and R, this vector and this vector is also 90 degree. Hence, this whole angle is 90 degree. If this is theta, theta is the angle made by the magnetic field, elemental magnetic field with the x-axis. If this is theta, this becomes 90 minus theta. And this becomes, again, this angle is 90 degree, it becomes theta. If it is 90 minus theta, then this becomes theta. Now let me write cos theta. If I consider the angle here, this is O, this is, you take this distance from O to this point P as x. O, you take this point A, the distance between O to this element is radius, and this is O to P is x, and this you can call some name A. OA equal to R, AP equal to small r. So if I consider right angle triangle here, because it's a right angle triangle, cos theta adjacent upon hypotenuse. What is adjacent? Capital R upon small r. Cos theta equal to R upon small r. This is a key, the next key to the learning process. Call it as equation 2. So let me cross check. Now what is R? According to hypotenuse theorem, capital R square plus x square. I can write it here. Of course, the place is less. Let me write it here. This equation is x square plus capital R square is equal to small r square. By Pythagoras theorem, I can have this relationship. Call it as equation 3. What is equation 3? Since it is a right angle triangle, capital small r square equal to x square plus r square. What is x square? It is OP square equal to x square. It is OA. This point is taken as A. This is r square plus x square equal to small r square. I have written here. This is the first step. As I said, the whole elemental magnetic field, this dB is divided into horizontal and vertical. The vertical components are, and the horizontal components are. The vertical component is dB perpendicular equal to dB sin theta. The horizontal component is very good. It is dBx equal to dB sin theta, cos theta, and call it as equation 4. Now we know that cos theta is equal to capital R upon small r. You sit here. I repeat, the theta is the angle made by dB with the x-axis. If this is theta, this remaining is 90 minus theta. This is again theta because the angle between this vector and this vector is 90. If this is theta, 90 minus theta, and this happens to be theta. If I consider theta, it is R upon small r. And already we have written, we know that if I consider right angle triangle OAP, this r square, capital small r square equal to x square plus r square. Yes, this is a simple mathematics. Now then r is written as under root x square plus capital R square. These equations I'll be putting here. I know what is small r. Small r equal to under root. Yes, let me write it. Capital R in the denominator x square plus r square 1 by 2. Now dB already I know. Now let me go for this equation. Equation 4 gives me dBx, the horizontal component of magnetic field, is equivalent to dB. dB means mu 0 upon 4 pi I dl. In the denominator you have x square plus capital R square. Because it was r, because r square equal to x square plus r square. Then you have a next formula into cos of theta. Cos theta is nothing but capital R in the denominator x square plus capital R square. So which is going to be 1 by 2. So finally it is 1 by 2. Its simplification gives you dBx horizontal component equal to mu 0 upon 4 pi I dl. In the denominator they get combined. It is x square plus r square 3 by 2. Yes, I stop here. Call it as equation 5. I repeat, we have small r square equal to x square plus r square. Substitute the value of r in cos theta and make use of this formula. This is a horizontal component. All the current gives rise to magnetic field, current in the wire. The whole magnetic field is joined to vertical and horizontal. The horizontal components will add it up. This is one quantity. Now to get the total magnetic field, horizontal magnetic field, I need to integrate equation 5. Once I integrate equation 5, I will be calculating finally what is the magnetic field at a point P. This is called magnetic field on the axis of a current carrying loop. Let me integrate equation 5, I'll get the final step. As I say, to calculate the total contribution at a point P, the total magnetic field, the total magnetic field at point P due to the current loop, is B equal to integration of dl. In the sense, integration of dBx. Integration of dBx is nothing but integration of mu 0 divided by 4 pi. Integration of mu 0 upon 4 pi. You have IDL R. In the denominator, you have a relation x square plus r square 3 by 2. Now, since this whole loop, the radius is r, the small element is dl, mu 0 upon 4 pi, I, r, and all these are out of the integration, left with only integration of dl is equivalent to mu 0 divided by 4 pi, I, r. In the denominator, I have x square plus r square 3 by 2, whereas the integration is over dl. And integration of dl is the total length of the circular loops. Total length of circular loop is 2 pi r. Hence, I can write this equation is going to be B equal to magnetic field B equal to, let me write it here, integration of dl equal to 2 pi r. This I will be substituting in my equation. Yes, let me substitute here. This becomes magnetic field B is equivalent to mu 0 divided by 4 pi. This, it becomes I, r, and you put it 2 pi r in place of this integration. In the denominator, again, remaining things as it is, x square, r square, it is 3 by 2. Now, these two people will celebrate. It's 4 pi, it's 2 pi, 2 and pi, left with only 2. The final relation simplifies to, look at it, it is I, r, r, it becomes I, r square, mu 0 upon 2, mu 0 upon 2, I, r square. In the denominator, you have x square plus r square, x square plus capital R square 3 by 2. This completes the equation. A small part, yes. Let me rewrite this equation once again, which gives you this B equivalent to, on the left hand side, it is, this gives you B equal to mu 0 upon 2, it is I r square. In the denominator, x square plus r square, it is 3 by 2. This completes the magnetic field equation. Magnetic field at a point P due to a current carrying circular loop along the axis at a distance r. From the center, it is x, B equal to mu 0 upon 2, I r square, x square plus r square 3 by 2. This is going to be my final relation, which is called equation 5. The last step is, instead of a magnetic field along the axis, magnetic field on the axis of a current carrying loop, if I am interested, what is the magnetic field at the center of a current carrying loop? Now, if x equal to 0, x equal to 0 stands for magnetic field, magnetic field at the center of current carrying loop, is When I substitute x equal to 0 in the formula, yes, the formula is b equal to mu 0 upon 2, it is I r square, in the denominator x square plus r square 3 by 2. If in this formula, if I substitute x equal to 0, because this expression is for a point P on the axis. This is magnetic field on the axis at any point P. This is called BP. Now, if x equal to 0, this whole equation reduces to magnetic field at the center of the loop at x equal to 0 is going to be mu 0 upon 2, I is as it is, r square as it is. Now, if I substitute x equal to 0, it becomes square is there, 3 by it nullifies, left with r cube. Now, r square and r cube will enjoy. Finally, after my class, we will enjoy. Yes, mu 0 upon, it becomes 2r and it is just I. So, final expression is B magnetic field at the center of the loop is magnetic field at the center. Center means here is given by B is equal to mu 0 I divided by 2r. This completes the whole expression for magnetic field along the axis. Magnetic field on the axis of a current carrying loop. This is the expression magnetic field at the center of a loop provided x equal to 0. This equation reduces to equation, simple equation, call it as equation 6. Already we have taken it as equation 5. Equation 5 is an expression for magnetic field on the axis of a current carrying loop, that is point P, whereas this expression is for magnetic field at a point P at the center of a current carrying circular loop.